Welcome to our weekly seminar, and we are delighted to have two fabulous speakers today. Also, hopefully you got the email, but there's other things going on this week. We have a big workshop on human-robot interaction and algorithms for human-robot interaction that's going on Wednesday, and then Friday night at the museum, the Young Museum, 100 Years of Robot Art and Science. Anyway, all this is online on the Cpar website. So without any further ado, and I don't want to take any of his precious time, I'm going to turn you over to the amazing Peter Abil.
Thank you, Ken. I got my mic here. All right, so what I'm interested in with my group is how to make robots learn. And the reason that's the case is because I think it's going to be the way to get robots to deal with large variability. There's quite a lot of other things to work on, too. But the thing I want to focus on in this short presentation is kind of the reinforcement learning approach to try to tackle this problem, where we try to get a robot to learn through its own trial and error. And so what I want to do in this presentation is, since many of you saw the presentation just 2 weeks ago at the Bear Robotics Symposium, or if you haven't, you can go check it out on video on YouTube, on my webpage. So what I want to do in this presentation is to dive in a little more detail on two of the things I talked about there. So the high-level picture is that in computer vision, we've seen the landscape change drastically from this kind of hand-engineered pipeline to a deep supervised learning pipeline since 2012. And then the question is, of course, can we do the same thing in robotics? Can we go from these highly hand-engineered pipelines with maybe a little bit of learning to pipelines that are fully learned? Of course, the big difference here is that learning for robotics means learning for control. If you make a mistake in a prediction in a supervised learning problem, there's no consequences in terms of the next thing you need to make a prediction on. But in robotics, you make a prediction, you take an action, you need to deal with the consequences of that for your next action, and this keeps repeating. So things could go unstable. You have a feedback loop there that you could drive the wrong way. In addition, the supervision is less explicit. Supervision in reinforcement learning is in terms of whether you have been doing well, whether you're in a good state or not, but it's not saying for every state what the right action would have been. And so teasing out what it is that you did that led to a state that's rewarded very highly is a hard problem. And that's what you need to do during learning. The other hard part is that you need to explore. You need to figure out where in the space you need to be to collect good rewards. Now, still, you could ask yourself the question, can we go directly from pixels to actions? Can we, for example, learn to play one of these games where the input would be pixel values, and then the output would be joystick actions, and you'd get to observe the score. And so you'd be playing with your joystick, you'd see your score change, and you'd hopefully learn what it is that you do with the joystick that makes your score go up and what you should do more of. Here's an architecture that succeeded. This was built by DeepMind, the DQN architecture, which goes from pixels via a convnet into scores for each of the possible actions. In their Nature paper earlier this year, they reported horizontal axis here is relative to human performance. This is 100%. So everything above here is above human level performance. And so they were able to learn with standard Q-learning, with a few tweaks to stabilize it. They were able to learn a deep neural net that maps from raw pixels to good joystick actions. And this is kind of surprising. What we've been interested in is actually take this to robotic control, which is still quite different from playing video games. So the kind of problem we've been interested in is, can you learn to control robots like these? Can they learn to control themselves through a representation that's a deep neural net that is a very flexible mapping from joint velocities and joint angles through this flexible set of mappings here to then means and variances on the controls that hopefully would do well at the task you care about. The way we start looking at this, well, the first thing you could say, well, why not just rerun the Q-learning approach from DeepMind? Well, two big challenges there. One of them is, how do you score every possible action? So we have a continuous action space now. Q-learning was outputting a score for every possible action. If you discretize this kind of space, it's much too high dimensional for that to succeed. So that wouldn't work. Another question is, how do you ensure monotonic progress? So often when you do this kind of research, it's very hard to ensure that your algorithm is improving at all times. For example, if you look at the DQN results, some students in my group tried to reproduce those results and actually weren't able to do that until DeepMind finally published all their tweaking parameter values, and then when they copied over those, it started working. And the deal is here that it's really hard to get that DQN method to work because there's a lot of tweaking parameters. And the tricky part is that there's no measure of progress there. You're not directly optimizing a measure of progress. You're optimizing some kind of Bellman error, which does not directly relate to performance unless you zero it out, in which case, of course, you'll have the perfect Q function. But it's hard to get there. And so since we actually, A, had a hard time getting Q-learning to work, and B, it's not clear how to score every possible action there, we started looking at direct policy optimization. The beauty of direct policy optimization is that you have an objective here, maximize expected sum of rewards under your current policy pi theta. What that means is that if you have a current policy, you can execute it multiple times. You can average the rewards accumulated over the multiple executions, and there's an estimate of the quality of your current policy. And then you're directly optimizing that quantity. So when you take a step, that quantity should improve. And this is very different from what you do in Q-learning, where actually you don't have this direct measure of improvement. A reason that this might work is that often representing good policies might be a little simpler than representing more complicated things like value functions. For example, linear controllers are known to work quite well for many regimes. And so if you represent your control policy as a deep neural net with rectifier units, ultimately what you end up with is a hybrid system of linear controllers. And what you're doing is you're learning which linear controller to choose when, how to divide up the space into where there should be different linear controllers, and you're also learning the linear controllers themselves. And so you're actually relying on what has already been proven successful in many situations, but you're learning it all rather than hard-coding a tessellation of the space and so forth. Existing work looking at policy gradient methods, so policy gradient means you would take the gradient of this objective and then take a step in that direction, have worked on relatively small examples, but gave a lot of challenges in higher dimensional problems. The reason is that it's very difficult to find good, large step directions. So if you have a gradient direction, you can always take tiny steps and repeat that many, many, many times. But the problem is that that would take too long in these high dimensional problems to get to a solution. And so what we were interested in is, can you make larger steps than just tiny, tiny gradient steps? And so to get there, what we did is we set this up as a trust region optimization problem, where this is still the first-order Taylor approximation, where we have a gradient estimate for the current settings of the parameter vector theta. And so this is the linear approximation based on that. But then here's a trust region constraint that says the KL divergence, which is a distance between two probability distributions, between the distribution over paths under the current policy and the distribution over paths under the alternate policy, theta plus delta theta, and we're optimizing over delta theta, has to be small enough. If that change in distribution is small enough, then that means you can trust this first-order approximation. And so because this measures where that first-order approximation is good, this allows you to quantify how far you can step. And in some directions, you might be able to step very far in theta parameter space, but you'll never be able to step very far in terms of changing your distribution over trajectories. So trust region deals with the fact that you have a sampled evaluation of your gradient. The gradient is only locally good, and once you change your policy, your distribution over states that you visit will change. Here's an example of the kind of result we got with this. So this is tested in Mujoko. This is a swimmer robot. And so this learned from scratch to make forward progress. Same for the hopper. The reward function is as simple as the further you are forward, the better. And the magnitude of the impact with the ground is being penalized. And here you'll see some of the learning in action. So initially, very first one, you see it just fall over. But then over time, it gets better and better and better. Every iteration means a new setting of the policy parameters. Per setting, it runs multiple trials. If you look at the learning curves for the hopper, so lower is better because we're minimizing cost here. Green and blue are two versions of the trust region policy optimization method. The other colors are other policy optimization methods. The horizontal bar at -1 is what you get if you just learn to balance. So just learning to balance, if that's this performance, once you're actually making forward progress, you'll do better than that. And you see that this learns a lot more quickly than these existing methods. You can also apply this to the Atari games, actually, even though that wasn't what we set out to do. You can set up a neural net that takes in pixels rather than joint angles and joint velocities, outputs discrete action scores rather than continuous actions, and it works comparably to the existing approaches on the Atari Games, the ones from DeepMind and from Michigan. With the additional beauty that it's actually easier to get to work because you're running a policy optimization, and so it's easy to track whether you have an improvement in your parameter settings and consistently keep improving as you proceed with your calculations. If you want to get this to work in 3D, you need to do a little bit of extra work. So what we're looking at here is, let's say we're still optimizing our policy, and this pi theta is a big neural net, and every weight in the neural net is an entry in theta. Trying to optimize pi theta to get good performance on, let's say, 3D walking. What the gradient looks like is something like this. So if you work out the gradient of this quantity, it'll be something that looks like this. What is this? It's saying it's the expected value of, and this is one term per time step, the gradient of the log probability of the action you took at each time step times, and this is then the future rewards you got from there minus the value from that state. So what this is measuring is the action you took at time t is looked at, and what's multiplied in is how much better you did than you would do on average if you did with respect to your current policy kept acting. So VST is here with respect to your current policy saying, on average, this is how well you would do from the current state. This is measuring how well you actually did. And so if you take an action that does better than you would do on average, then you want the probability of that action to go up. If you took an action that does worse than you would do on average, you want that probability to go down. That's exactly what this equation will do for you. It's an expectation up front, so you'll need to do multiple rollouts under the current policy to estimate this reliably. Now, this is what we used in the trust region policy optimization. What we used to actually get it to work for 3D walking, which is a higher dimensional problem and has more failure cases or more ways of going wrong, we have to do 2 tweaks. One thing is to, rather than just using this estimate here, future sum of rewards minus value, we also looked at other estimates. So if you look at just future sum of rewards, that's a very kind of noisy estimate because it's one rollout you're considering. What you could do instead is you could say, let's take the reward in the first next step, see where we land, and then take the value at that next state and use that as your estimate rather than sum of all rewards. Or you could take rewards at the first 2 next steps and from then on take the value function. So there are many, many choices you can make in terms of how far out you want to take rewards, and from then on use the value function. And so by doing an exponential mixing between how far out you take rewards versus value function here, you get an interpolation between traditional actor-critic methods and Monte Carlo estimates, which works better than either one of them and makes a big difference here. V here is the value function, which estimates, or well, ideally would be exact, but in practice estimates the expected cost to go under the current policy.
When you are looking this gradients method, which that's what you are doing, are you looking for negative increments?
So here we're just estimating the gradient, but then once we take, if we're minimizing expected cost, we would step in the negative gradient direction. But this is just the way we're estimating it. The other thing we did to get this to work is not just use a trust region for the policy optimization, but also for the value function fitting, which is a pretty natural thing to do, but people aren't really doing in general. So when we fit this value function estimate here, we estimate a trust region based on the empirical variance on the previous batch of data, which will determine how far we can move our current estimate of the value function. With those 2 pieces in place, you actually get this kind of behavior if you use it on top of the trust region policy optimization, which has it learned from scratch how to optimize reward, which is defined as the further forward, the better, and the higher impact with the ground, the worse. And it realizes that some kind of locomotion is the best way to optimize this reward. In terms of amount of experience, every iteration consists of 500 seconds, if it were real time, of rollouts under the current policy. Those 500 seconds of rollouts are used to estimate that gradient and estimate that value function and then an update is made. Yes, Ken?
So if my intuition is that the value function is pretty unknown at the beginning, right, because you don't have a lot of data. So
Correct.
It's littler steps. And then as it starts to make progress, the value function gets better modeled, and so you can take bigger steps. Is that fair?
There is truth to that, because your variance on your rollouts will be higher initially. And so the empirical variance on the fitting will likely be higher too. And so you'll actually be allowed to make larger steps then. Unless it happens to be the case that you always initially fall over really badly. In that case, the variance will still be low. So it's a little more subtle than that. It's not just about the magnitude of the value function, but also if it's always bad, it's again going to have low variance.
Right, but as it starts to improve, it's sort of your step size gradually.
It'll start zoning in on the right thing. That fitting error will go down, and it will make smaller and smaller steps. Yes, absolutely. So it's interesting to note that, I mean, you can do a lot of things here. You can actually, it's still a valid policy gradient if you leave this out, it turns out, the subtraction of the value. It's still an okay equation to use, but it will be a much higher variance estimate, because now you're just changing the probability of actions where good actions are made much more likely and bad actions are made just a little more likely. Whereas if you subtract out the value function, you make good actions more likely and bad actions less likely, which is a better thing to do. We've seen this last time, so let's skip this. Now, question to ask is, well, can we get this to work on a real robot? And actually, Chelsea who's here has worked on some of that. And the big difference there is, of course, the number of rollouts that you can attempt on a real robot. You can't do 500 seconds of rollouts that easily, and then maybe 2,000 iterations would add up to a long time. For example, for the walking, it would take 6 days, which isn't too bad. I mean, at this point where it works, maybe we should just try it and get a robot and try it out for 6 days and see if it learns to walk. But if you're still developing your algorithm, it's really hard to develop an algorithm that takes 6 days of turnaround before you can expect it to succeed. So we see here is the PR2. And some of the tasks we might be interested in is getting this block into the matching opening here. What we looked at there is something called guided policy search. What that does, it's a different approach from the trust region policy optimization. It assumes we have access to a few things we didn't assume access to in trust region policy optimization, but we still try to get out a neural net that is a good policy. Policy search would try to learn that directly, deal with complex dynamics. A complex policy has to be found. That's a hard thing to do. Supervised learning is a lot easier. If somebody just told you what to do, you don't have to deal with the dynamics. You just need to learn the mapping from state to action, and that's understood pretty well at this point. The question is, how are you going to supervise it? One way would be to get trajectories. And you could get trajectories by people demonstrating, but if you want to do it automatically, you could get them by trajectory optimization. They get computed for you somehow. That trajectory optimization would deal with the complex dynamics, but wouldn't have to find a complex policy. It just needs to find a trajectory, which is much simpler than finding an entire feedback policy. And so that's easy. So you'd have a trajectory that has been optimized. You feed it into your neural net as training data. And hopefully then the neural net can generalize, if it's seen many trajectories, to also do the right thing in new situations. Okay. So one question you could ask yourself is, how do you find good trajectories? Let's say you want the PR2 to succeed at a single task. Insert that block into a specific opening that's in a specific location. How do you get that to work? Okay? So what you want, ultimately, is some trajectory that is encoded by Q here. So some policy that generates executions along a trajectory, so that's Q. And so we'll collect a bunch of trajectories. Let's assume we have some policy. We executed, get a bunch of trajectories out. That's our database of trajectories. We then say, OK, these didn't succeed, so let's fit a dynamics model at each time step along those trajectories. Once we fit that dynamics model, we now can simulate what the robot would do along those trajectories. It's only locally valid, but locally it's a reasonable model if we had enough trajectories. We can then use dynamic programming, for example, iterative LQR, or kind of even just a regular LQR backward pass, because it's a very local model, to find a sequence of linear feedback controllers that are better than what we had before according to this model. Now, of course, the model is only locally valid, so there'll be a line search parameter there to make sure that we don't go too far away with our new optimal trajectory from what we had before, because otherwise, in the real world, it wouldn't be good. It would just look good in simulation. Once we have done that the right way, we can then execute that new sequence of feedback controllers get new data, and keep repeating this. And so that's a way to iteratively get better and better executions. Yes? So the way we do that here, because we get executions of a policy that's pretty close to deterministic, not exactly deterministic, but close to deterministic, the trajectories are very similar on every execution. And so we fit a local linear model at every time step. So we fit very simple models, but they only have to be valid for a particular time step and in that part of space. Because when we re-optimize our policy, we have a trust region constraint that doesn't allow the policy to move away very far from where we were before. They take everything into account because the data we have here is the joint angles, the joint velocities, the torques commanded to the robot. But we also, if there is contact with the environment, that will affect what the next state of the robot is going to be. And so in that sense, contact is taken into account too. That's all there because we're looking at a mapping from current state and control inputs to next state of the robot. Ken?
Just for the robot.
We only look at state variables related to the robot here. Yes.
How do you do the segmentation? I'm just curious into these regions.
Oh, so this is just time indexed. And so because it's a computer that's running the controller, the time indexed modeling works out fine because there's a lot of consistency.
Okay, so you just say within this time period, I'm going to just keep looking. Okay.
Within this time period, you take the data that was at that time slice across your multiple trajectories. It's not a lot of data. So there's a little extra trick we play to get this to work in practice is we use all past data we've collected, not just under the current policy, but all past data. And a lot of that past data is not going to be along the same path and is going to be less relevant to modeling along the current path. So we use that past data not based on its timestamps, and we don't use it to directly fit the linear model, but we use it to build a Gaussian mixture model prior for this fitting process. And that allows it to fit with a small amount of trajectories.
I'm still confused. You have a machine which you can measure the hell out of.
Yes. Mm-hmm.
Therefore, you can get a very detailed model. Therefore, you can get predictable trajectories. So why do you need all this Mickey Mouse?
So the reason you want this is, first of all, this procedure gives you what you just described. So you get that model.
Right.
So you're getting it. You're not losing it. It's actually taking advantage of the fact that there is a model and that it's recovering it. What it does in addition, the dynamics that's learned accounts for the contact. And so if you look at the learning process, you'll see maybe the first 5 iterations, it's refiguring out how its arm works. But then the next 35, which is the remainder stretch, it's figuring out the contact dynamics between the objects that it's manipulating. And so that's really where it's spending the bulk of its learning time, is learning about contact dynamics between objects it's manipulating. And so if you get a new set of objects, you have to somehow figure out what that would be for those objects. And here it'll just learn that for you.
Because he's got a very uncertain robot, right? That's a big problem. There's a lot of variation in that control.
Well, I would argue that that's actually not true. It actually relies on the fact that the robot is relatively consistent in these executions.
I think what he's arguing is that the internal forces that come from the object grasping will vary, and you don't know them a priori. Now, I dare to challenge you next semester because that's exactly what Shankar and I are going to teach.
All right, so we should do a face-off at the end of the semester. We'll have all your students in a room for a day. We'll have Chelsea in the neighboring room for the same day, and we'll define a task nobody knows ahead of time, and we'll see which robot comes out victorious.
Yeah.
We will time the programming amount of time. You can spend only 10 hours programming, including robot trials, and we'll see what happens. Yes, I think what we should do is we should stop here to give Florian enough time. I think we had some good discussion. That's the most important part.
Totally.
And let's switch to Florian.
Okay, so while we're switching on Florian, Peter, I don't mean to
Sure.
cut you off here, and what we're hoping is that you will have some slides, right?
Sure, yeah, I'm happy to share this one.
Of papers that Peter and his group are writing that are extremely relevant to this course. Very exciting, and they're getting very, very promising results. I think that this exactly what Lucian brought up, and I'm so glad you did, is that this is really challenging the conventional wisdom about analytic methods, and it's at the heart of the debates that are facing robotics right
I
now.
really think it's a mistake to say my truth is the only truth. You know, like
No, but it's still helpful to have come from a position and then see.
Yes.
And I think what we're suggesting actually is the first time I've heard of this, but I think that maybe it is seriously, an idea to take up a task,
absolutely.
set it up in an environment where it's an entirely new task, and then have it as a competition. I think it would be actually fascinating.
It's not even a competition. It's really through, you know, with learning where the advantages and disadvantages are.
Well, that's where exactly.
That's my approach. I'm not competing.
Come on,
You know,
you're with Chelsea.
I was there 30 years ago, so it doesn't matter. But the point is that we want to find the truth. Okay? And we want to understand what works, where the pitfalls are. And you know, there is not one way to solve the problem.
No. I think that's exactly right. And also but comparing apples to apples is interesting, right? So really trying to get one task.
Yes.
So let's make that an objective for this. Let's really think about that.
That will be a nice paper.
All right. Yeah, you all were here. You heard it. The origins of this. Very good. I think we have it recorded, I think. All right. So, thank you. Did we say thank you to Peter? Okay, and that's just a sample. Again, remember, the whole point of these is to give a taste of research. We're not able to really go into extensive detail, although maybe next semester we're going to have longer talks. But this is really sort of basically give a taste and whet the appetites. Florian is next. He's a postdoc. He's visiting from Sweden. He's been working in our group with the AMP lab and is going to talk about big data and graphing. Florian.
Thank you. Okay, so I will tell you a little bit about large-scale data and grasping under uncertainty. So some of the goals that we're working towards is to free robots from cages like these, essentially. This is an example picture of how robots are being used in the automotive industry at the moment. And, of course, the problem here is that often these robots don't actually have sensing on board, and they just repeat the same task over and over again in a very manual, programmed fashion. So the goal here is to use sensing and to allow robots to operate both in the industrial setting and also in the home setting autonomously and to grasp and manipulate objects that they encounter and might not have seen before. So the work that I'm talking about today involves a lot of people here at the lab, and in particular some of the PhD students in Ken's group, and Ken as well. So let me give you an overview of the plan for the talk today. So I will start off reviewing some of the more classical ideas on grasp synthesis based on force and wrench analysis. And then I will go on to discuss a few of the problems with this type of approach and how we're trying to deal with these problems, in particular understanding uncertainty and robustness problems that arise in this approach. And then finally, I will talk about a very recent work around DexNet, which is a large-scale approach to grasping that we're working on, and which involves a large collection of mesh models and grasps that we are assembling in order to learn about grasping at a scale. Okay, so what is the problem here? We're interested in the grasping problem. That is, we would like to teach a robot to reliably pick up an object, manipulate it without any slippage or failure modes where the object just falls out of the hand. So how can we achieve this? If we look at the literature, there's a very long literature on this type of problem. And the framework that has been used in the past 25, 30 years is that of point contact-based grasping. So here are three pictures of some of these simulation environments that are being used today to analyze robot grasps. So OpenRay, for example, GraspIt has a long history as well. And what you can see here is that all these models are based on a point contact model for the grasp. So highlighted here are a bunch of friction cones at each of simulated contacts here. And these friction cones correspond to a Coulomb friction model that's assumed at each of these contacts. And we're interested in trying to find contact configurations such that the object does not slip out of the robot hand. Okay, so what is a grasp? Let's first formalize this according to this type of approach. So one way of thinking about it is to think about a grasp as a tuple of point contacts between the robot hand and the object, where we have m contact configurations in three-dimensional space. Then we have m surface normals at these contact points, and then finally a center of mass of the object. And for many of these classical approaches, this is the type of data that you need to, first of all, understand what the contact and in particular the grasp configuration here is. Now, once you have that, you can start to think about wrench spaces. And in particular, you can try to understand what are the possible forces and wrenches that can be exerted by a grasp like this. And this leads to the notion of a grasp wrench space, which is a six-dimensional convex hull configuration, which corresponds to wrenches that can be exerted at all these contact points. Let's call that S of G. Now, more than 24 years ago, Ferrari and Canny defined a metric for this type of grasp analysis, which in essence looks at this convex hull in 6 dimensions and tries to see whether the origin lies inside this convex hull. And that exactly corresponds to the ability to counteract wrenches that are being exerted on this object by applying forces on the contact points. And this grasp metric here by Ferrari and Canny looks at the largest sphere that sits inside this convex hull in 6-dimensional wrench space. Okay, so this is a nice kind of analytic way of thinking about grasping. And to some extent, you could ask yourself, okay, we have got an analytic description now which corresponds to a physics model. It might potentially not be 100% correct because we're talking about point contacts rather than surface contacts, but it seems to be a good description. So is the grasping problem solved because of this? And 25 years of research after this have not really concluded with an answer here. So this is static, yes.
The object is no gravity.
Yes, static grasping. So there are many problems with this type of approach. So I will try to dwell into some aspects of this. For example, the basic properties of this type of grasp quality. What do we actually know about it? And then I will focus on some of our recent work which tries to attack the problem of robustness under uncertainty for grasping. And finally, I will talk a little bit about how we can actually determine optimal grasps. Okay. So let's look back at this kind of classical grasp quality measure. What are its basic properties? So I talked a little bit about these friction cones that are at each of the contact configurations. And in order to actually compute this grasp quality measure that has been suggested by Ferrari and Canny, what you have to do is you have to reason about these convex hulls here. And it turns out that's actually not so easy because this here is a convex hull of some analytic set. It's not necessarily a finite set of points a priori. But what you can do is you can approximate the friction cones at each contact point by polyhedral cones, as I indicate up here, where you choose, for example, 3 edges in the cone, or many more if you like. And this leads to a convex hull, which is actually just a convex hull of a finite set of points. And about these we can reason very efficiently. And this is, in fact, what has been done in the last 25 years. People use these kind of approximations in order to reason about grasp quality. And that's called a grasp quality measure which approximates the friction cones by L polyhedral edges, QL minus, and the original grasp quality measure by Q. Okay, so this is kind of the quality metric people might want to use. There are many others, of course. So what can we say now about this? So first of all, let's look at just some simple mathematical properties of this grasp quality metric. First of all, what is the space of grasps abstractly? One way to think about it is as a domain for m contacts, as I indicated before, where you have m contact points, m unit normals, and a center of mass. And this grasp quality function that I talked about earlier is a function defined on this domain. So the first surprise is that this approximation by polyhedral cones is actually not a continuous function on the space. And this is something that we observed in a paper in 2013, which is kind of interesting because a lot of prior art was using implicitly the continuity, for example, in gradient-based optimization. The assumption somehow was that this approximation was a tame thing to consider. The underlying analytic graph quality is actually a continuous function, and it's differentiable almost everywhere, so it's relatively tame. Furthermore, you can ask about error bounds. So how far are we actually off when we compute these approximations? And we developed some error bounds for this, which rigorously relate the worst-case error to between the approximation and the underlying glass quality metric. OK, so we have a little bit of theory under our belt now. What can we do with this? You can develop upper and lower bound algorithms for this, which is kind of interesting. But really, we'd like to understand more of the global properties of this glass quality measure. So one approach you can take is you can just sample a lot of graphs and try to understand what kind of things jump out at you. And this is something we looked at. We looked at 100 million synthetic grasps, independent of the notion of shape. So here you just sample point contact configurations, the center of mass, and these normals that I described. And what you find is that there's some interesting properties of grass quality that you can study. So for example, the distribution of grass quality across a uniform sample of these random graphs is kind of interesting. It's heavily tipped towards 0. So most grasp hypotheses that you might sample are actually unstable. There's a very strong dependence on friction coefficient as well. Of course, as the friction, as you have fewer and fewer, less and less friction, you're less able to kind of manipulate the object because of that. And very interestingly, what you find is that the grass quality is actually a rather tame function. It, in particular, seems to be Lipschitz continuous. And this is something you can gather from this kind of statistical analysis. And in fact, we then proved later that it is a Lipschitz continuous function with a particular Lipschitz constant. Now, this might seem a little bit esoteric to you, but let me tell you why I think this is an important property. So if you have some function here, for example, this indicated by the graph of this bold graph here, which you can approximate from above and below. If you know, first of all, the errors on this approximation, and secondly, the fact that this graph here corresponds to a Lipschitz continuous function, you're now able to make inference about nearby grasp configurations. So in particular, if you sample a stable grasp, if you perturb the grasp a little bit, this Lipschitz continuity implies that the quality measure does not vary too wildly. And this is something that's important for the kind of data-driven paradigm that I'd like to talk about later. Yeah. Yeah, that's an excellent point. So it's smooth with respect to, it's Lipschitz continuous on this domain. So you have to vary the normals continuously. So if you have something like a box, there's a discontinuous jump in normals, which causes this kind of behavior you're talking about. However, under uncertainty, there's an interesting fact that the uncertainty starts to smooth out these corners. So in a way, you can still think of this as a relatively tame function.
So, excuse me,
yes.
I'd like to understand this. So the red and blue points are points, grasp points on the object.
OK, so
and therefore, I can move them on that line.
So the way to think about this is that this is just a visualization of this high-dimensional space of contacts and normals and centers of mass. And if I'm able to sample a grasp which has a certain grasp quality in that space, that's a point corresponding to this, which has positive grasp quality, this implies that in a metric ball around this configuration, your grasp will remain stable. So small perturbations of grasps remain stable.
So this is still the conditions are that I have an object and I can grasp it and just stabilize it.
Yes.
Correct? Okay. Thank you.
OK, so I talked a little bit about grasps independent of shape. In a way, we had this domain here. But really, we'd like to connect this up with the notion of the space of all shapes that we encounter in reality. So we started to look at this, starting from this very simple point contact-based approach, and went towards looking at shapes that are defined in terms of cylindrical coordinates. And this led us to the notion of a grasp moduli space. So in simple shape families, for example, with cylindrical coordinates, you can rigorously define what it means for two shapes to be close to each other. There's a natural metric on this. And you can combine this with this kind of Lipschitz continuity intuition to understand the continuous deformation of both shapes and grasps in that space. So for tame functions, this means that if you have a lot of data available on some shapes that you've seen before and you encounter a new shape that's very nearby and a grasp configuration that's very nearby to a grasp you've seen before, then these kind of Lipschitz arguments allow you to reason about the stability of a newly seen instance. However, our prior work here was only on analytic shapes that were described in terms of cylindrical coordinates. So this is still a rather simple model. So let me talk about how we can do this now in a data-driven fashion. Okay, one more point I'd like to make is that in this space you can now start to think about different types of perturbations. You could either think about perfect perception of a shape where you perturb the contact configurations a little bit continuously. And due to the Lipschitz continuity, this allows you to reason about how much grasp quality changes as you move along the surface here. You could, however, also have cases where your perception of the object is noisy. If you can bound that, then Lipschitz continuity again will allow you to reason about the perturbation in grasp stability. Okay. So, of course, we still haven't really solved the whole problem. Grasping is very complex. Let me tell you a little bit about robustness under uncertainty. How can we really try to make progress with this difficult problem? So if we look at real-world data that a robot might perceive, you might be in a rather bad situation where you're, for example, looking at a bunch of objects which are transparent or have high specularity. And in that case, the typical type of data that you get back from this kind of scene might look like this. So this is data from a Kinect depth sensor. So faced with such kinds of data, of course, we're not able to precisely estimate normals and point contacts here. So we need some kind of probabilistic way of reasoning about this type of sensor data. How can we do this? So one approach that we took in recent work, which was led by Michael Lasky at CASE 2015, was to look at 2D objects in particular and to start to define a probabilistic approach to grasping here. And what are the components of probabilistic grasping in this setup? We'd like to be able to have a probabilistic model which takes into account both the shape of the object, the pose of the object, which might be perceived up to noise, and also the approach of, in this case, a parallel jaw gripper on the object. So all these quantities here are modeled up to noise only. We're not able to perceive them perfectly. And in addition, we only have an estimate of the friction coefficient. We are not assuming that we have a perfect knowledge of the friction coefficients at the point contacts. If we have a graphical probabilistic model that describes this, we can then start to talk about the probability of force closure rather than the deterministic force closure, which is what the prior models have been assuming. So talking about probability of force closure is useful in this setting. And we looked at a particular approach to optimizing the expected probability of force closure. And for this, we went back to the literature and looked at multi-armed Bandit models. Multi-armed Bandit models have a long history, starting in the 50s, which describes scenarios where you have a discrete set of choices. And in this case, you can think of them as arms of casino slot machines. And your goal is to optimize the expected reward of pulling one of the arms or choosing one of these options. And all that you can observe is whether you get a reward by pulling this arm. And you do this iteratively and try to find the arm that has the maximum expected reward in this procedure. Okay, what does this mean in terms of grasping? So multi-armed bandits for grasping, we can think about like this. So each arm in this case is a candidate grasp that you might want to evaluate probabilistically. And at time t, we're going to select an arm to sample to try out. And our goal here is, again, to optimize the expected probability of force closure. So trying out a grasp can mean in simulation we're going to evaluate a probabilistic force closure quality, for example, based on the Ferrari-Kani metric that I talked about earlier. Or it could mean in reality really trying out a grasp on a real robot. There are many algorithms for performing multi-armed bandit optimization, Thompson sampling, Gittins indices, and so on. So our approach here was to look at some of these techniques and to see how they perform in a simulated environment using a grass quality metric which is based on Ferrari-Canny. And what we found is that both Gittins indices and Thompson sampling were actually quite successful in determining good grasps on these kind of probabilistic shape and grasp descriptions. However, if you look at this plot, what you note is in order for these to converge, we need a lot of trials. So here we have 1,000 trials, which is fine in simulation, but which poses a problem in reality. We don't really have the resources to test 1,000 trials on a robot necessarily. So the next question then was, how can we reduce the number of trials needed here and still get convergence in a fast manner? And for this, I'd like to talk a little bit about scaling effects in computer vision and how this could have an influence on what we're doing in robotics today. So let me just go back a little bit in history. If you look at computer vision in the early days, starting in the 90s and 2000s, there was this development of initial databases of images that were being used for benchmarking of computer vision algorithms. And this started, for example, here with this data set of blob worlds with 2,000 images in 98. Then they moved to 10,000 images in 2002. And this kind of development continued until present time, where we're now with ImageNet in the range of 80 million images that are available. And this whole development was, of course, caused, at least in part, by the explosion of data on the internet that's freely available. So comparing computer vision 10 years ago to today, there has been this rapid shift, in part due to the deep convolutional neural networks that have been used. Yeah. And this kind of has led to exciting progress in that field. If we look at 3D data, there's a similar development. For example, the number of objects on Thingiverse has exploded. We're able to now get large collections of data available on the internet. And our approach here is to use this kind of data to build a large-scale network of grasps and shapes, and we call this DexNet. Currently, this has about 10,000 meshes, 2.5 million grasps in the database. And we have recently submitted a paper which looks at using this kind of data for grasping. The key components of this approach is to model the expected probability of success of each grasp candidate using beta distributions, which are simple two-parameter distributions that can model the likelihood of a grasp to succeed. And we're combining this idea with so-called correlated bandits. So what's the idea here? You have some object. Imagine a one-parameter family of grasps rotationally around this object here, just parallel jaw gripper grasps. As we vary the angle of this grasp, we have some varying probability of success in terms of grasp quality. We could apply the standard Bandit algorithm and sample discrete candidates of grasps here. As you iterate over trying to grasp one of these, for example, let's say we try to see whether this grasp candidate here succeeds. After updating the multi-arm Bandit algorithm, you will get an update in the probability of this grasp to succeed. This will change the expected reward of that particular arm or bandit. Now, the problem with the classical bandit literature is that a change in expected reward of this arm here does not have an effect on the nearby grasps and shapes that you might want to consider. In particular, in this case, we really want to update the nearby grasp that seem to have actually a better true probability of success. And correlated bandits allow us to do exactly this. So the idea here is that we are now modeling the probability of success continuously. However, we're choosing a discrete set of arms that we want to consider. And as you update one of these expected likelihoods, you're also updating nearby grasps. Let me just give you very quickly the intuition, because I don't have too much time. So how do you specify nearby here? The idea is to use this idea of moduli spaces again, where you have a continuously varying family of both shapes and grasps. And you define a similarity metric on the space of shapes and grasps, which in our case was composed of three main components. We look at phi1 here, which is a similarity metric defined in terms of point contacts of the grasp configuration, Then we have phi 2, which depends on local shape patches of the grasp neighborhood. And then finally, phi 3, which is a global shape similarity metric, which uses multi-view deep convolutional neural networks to get a featurization of the global shape properties. And this is then reduced in dimension to about a 100-dimensional feature describing the global properties of the shape. OK, so we have these three feature vectors. We stack them together, yielding a similarity metric. So Y here is both the shape that you want to grasp and also the local contact description of that grasp. K of Y gives you a normalized score between 0 and 1. And using correlated bandits, we're able to update the belief about nearby grasps as we get new data coming in. And this could be either from simulation or from real-world experiments. And let me skip some of the details here. Just quickly, some results. So the key take-home message here is that having a lot of data really helps. In particular, we compared our algorithms for a database with about 1,000 meshes in there to a database with 10,000 meshes. And what we find is that the optimal grasp is found, or a close to optimal grasp is found much faster than if we had little or no data available. So these two plots here are multi-arm bandits algorithms without prior data. This one here is with 1,000 objects in the database. This is with 10,000 objects in the database. And note here that this is now in the realm of possibility for real-world execution as well, which makes us very excited. Here's just a visualization. Nearest neighbor lookup with the deep CNN. If we have a network of size 1,000 for this query object, we get this nearest neighbor here, which is not quite completely close to it. But as you increase the density of objects, you get better and better matches. Here's just a simple visualization of different algorithms. If we use a lot of data, we find robust grasps which seem to correspond to intuition. So here the grasp is applied at the center of the object, which is naturally in a flat area, which is naturally an area which is very robust to perturbation and noise, compared to this type of approach here, which doesn't use prior data. Just a quick note about ongoing research to give you a snapshot. So we're currently looking at further scaling the type of work that I've described. In our prior work, we actually used up to 1,500 Google Compute instances to optimize these graphs, to simulate graphs and so on. And we're now pushing this further using technologies such as Spark and, again, the Google Compute engine. And another important aspect of our work is to look at real-world execution. As I said before, multi-arm bandits are very interesting because you can replace the simulated stability metric by real-world experiments, for example, and this is something we're looking at with this kind of setup here. The goal here being that we can execute a lot of grasps and really get the data scale up for future experiments here. So just to mention, the DexNet project has involved a lot of people, but I'd especially like to thank Jeff Mahler, who has been the lead author, and he's in the audience here, and also Michael, who has been working on the Bandit algorithm, especially for prior work. Thank you.